Yeah, good morning, everybody, and welcome to the next lecture in Bioprocess Engineering. Last time we have talked about kinetics. Today we will talk about kinetics, and the good news is there was no homework. So therefore, we have no homework to discuss.
All examples in this section are based on the Bioprocess Engineering Principles, 2nd edition, Academic Press from Pauline Duran. The solution path is also depicted in this book, so please refer to this book for details, and it's again a warm recommendation to have a look in this book.
So let's start right away. I already said we go for kinetics. We had talked about yield last time, and now we come to cell growth kinetics, which is of course as the yield based on the basic reaction theory. Now, okay, here we go. So let's start with a curve all of you have already seen. How does batch growth looks like? Kinetics in cell growth is based on the basic reaction theory. So therefore you can handle cell growth similarly, and you can handle it similarly to enzyme kinetics, applying this basic reaction kinetics. That's the good news. So the first chapter we did is not completely useless what we did. Now in batch culture, obviously you will observe the well-known growth curve. Usually this will be completely interactive. However, I know you are experts, so no need for large interactions here. All of you know how this typical batch growth looks like. You have this lag phase and so on. Now let's have a look here how this then turns out. So we start with a lag phase. If we plot t versus ln x, you remember if we plot it versus x, we will not be able to see with our eyes the exponential phase. Then the next phase is an acceleration phase, and we then come to the exponential phase, and there we have a linear correlation between t and ln x in a batch culture. And finally we come to a phase where the growth declines because my seed source is expired, and we come to a stationary phase where nothing happens, and if we forget our culture, then we might even see a death phase. If you see this in bioprocess engineering, you should look for another job. Usually you work not with cultures going into death phase. Often you always stay in this exponential phase and then transfer it to the next bioreactor. But sometimes it also requires to go to the stationary phase. For example, in our tumor vaccine, we need to go there because only in the stationary phase, when the cells get starved, we have the induction of the SPY1 pathogenicity island of Salmonella, and this is what we need, otherwise the immunogenicity of the strain will be lower. So this means it's not always that you have to go exponential. It depends on your strain. So you, of course, also in bioprocess engineering, you require a knowledge of microbiology, otherwise you cannot work properly. Okay, so this is how the cell growth curve looks like. And of course, if we look now at the specific growth rates, the specific growth rates are 0 in the lag phase and 0 in the stationary phase. In the exponential growth phase, we have a specific growth rate which is equal to μmax, and of course in the decline and acceleration phase it's below μmax, and in the death phase specific growth rate is even below 0. That's clear. And here in the acceleration and decline phase, of course μ is no more constant. In the exponential growth phase, μ is constant and is μmax. And you remember, of course, we have talked about how to calculate exponential growth. We can have a look what we have said in basic reaction theory. We have deduced based on the unsteady state mass balance for an open system, we have used for this general irreversible reaction, which is of course also a growth reaction, the following rates. So we have for RA, we have RA is equal to minus dMA dt. And if I have growth, my biomass is in general here. So I have here my substrate and maybe my nitrogen source. Then I get my biomass product and so on. So it doesn't matter. But at the end, if Y is my biomass, I get Ry. The rate of formation of biomass is dMy dt. So this is what we can directly use. And if the volume is constant, I can say that the volumetric rate is dCd. For Y, it is plus dCy dt. For A, it's of course minus dCy dt. So this is my volumetric rate, and I can directly use that to go to the calculation. So we set our Rx is equal to dx dt, because we always abbreviate our concentration of biomass with a little x. And now we also know that it's a first order reaction. So this in other words mean at the same time Rx is equal to or proportional to the biomass concentration and the specific growth rate. So we can write dx dt is equal to mu x. And now this is of course volume constant in batch. This is what we have taken from our basic reaction theory. And now of course we can simply solve this equation. So if we separate the variables, so we have dx divided by x is equal to mu dt. And of course if mu is mu max and therefore it's constant, what we can do is we can take out this mu out of the integral, and let's do it. So we write the same here, dx x is equal to mu dt, and now we can simply solve and integrate and now just use x0 to x as borders, and here we start from 0 and go to t. And of course then here we have ln x minus ln x0 is equal to mu t minus mu fold 0, and that's of course the same. And then we just rearrange, and we have ln x x0 is mu t and to the power of, and therefore we have x is equal to x0 fold e mu t. And this is of course our basic equation we have already deduced in applied microbiology. Now this is this equation describes the exponential growth in a batch culture, in the exponential phase, because there we have mu is constant. This is very important. This only is true if mu is constant. You remember that. And of course also here we should see the same. And of course, yes, we come up with this equation. And based on this equation, we can also deduce doubling time if we just here say x0 is equal to x0 and so on, and then we end up with the doubling time ln2 divided by mu, and this is also what you already know. Now, what is important is we always say mu max is in the exponential phase in batch culture, we are at a constant specific growth rate, and it is mu max. But where does it come from? Now this comes from the Monod model, and the Monod model is a model assuming a balanced growth model, that the cellular composition of biomass remains constant, specific rate of production of each component in the culture must be equal to the specific growth rate mu, as getting this equation. Now if we assume that we have limitation just by one substrate, maintenance is negligible and we have no inhibition and so on, then we get a saturation kinetics, and the saturation kinetics goes in this equation. This equation has been deduced empirically. So you remember with Michaelis-Menten, when you had your enzyme kinetics in biochemistry, most likely this equation of Michaelis-Menten was deduced because you could deduce it from the active centers and so on, the dissociation constants, association, and the reaction constant, and then assuming what is faster, what you can neglect, and so on. And at the end, you came up with an equation which looks very similar to that. You just had, instead of the mu and mu max, you had speed, V and V max, and of course then you have the Michaelis-Menten constant, but at the end it's the same. My bet, by the way, is also Michaelis-Menten had observed this equation empirically, and later on they deduced an elegant approach how to derive that from some theoretical assumptions. We don't care how it worked, but at the end, what you see if you plot a normalized version of the substrate concentration divided by the Ks and mu divided by mu max, so you will end up with, if you are at mu max, you are at 1. And if you're close to your Ks, if your substrate concentration is the same as Ks, you are also at 1. You see that you will get this curve. And you also, of course, realize that if your S is in the range of 10-fold higher than your Ks, then you are practically at mu max. Now it of course depends on what is the dimension of these Ks values, and indeed the Ks values are very slow. So you see in case of Saccharomyces we're at 25 milligrams per liter. E. coli, we are at 4 milligrams per liter. Of course, it depends on what we have as a limiting factor. So you see phosphate is very efficiently taken up. So you see a certain range of Ks values. So hard substrates who have higher Ks values, glucose as an easy substrate, the Ks values are low. And of course, you see if you have a growth of E. coli in your culture, you don't start with 0.004 grams per liter glucose. This is nothing. You have 20, 30 or so grams. This is more than a couple of thousand-fold higher than the Ks value. So this means when you start to reach this low Ks value, the fast-growing, exponential growing culture will rapidly consume that, and then of course it's over. Then so before it starts to adapt the growth rate according to the Monod model to the substrate concentration, it's just consumed. So that's the reason why during a batch culture you have, during the whole exponential phase, you have a constant mu max mu value, which is mu max, because the Ks values, at least for the standard substrates you use in the cultures, are so low. And of course, this is also true for yeast and so on. Okay, we can look at examples with respect to cell growth kinetics, and one example I want to show to you, but I don't want to calculate that. I just want to show it, and the result is plasmid instability. Often you have recombinant cells which are used for production, and if these are E. coli cells or so, your standard, what you do is you put in your expression plasmid, and this is what you use to produce your protein. If you can integrate that into your genome, or this can stay there as a plasmid. Now, even though if you have a good origin and if you have a good stabilization, there's a certain probability to lose the plasmid. This is not true for balanced lethal systems, but usually in production you don't use balanced lethal systems. This means that a certain amount of bacteria is likely to lose the plasmid after division. Yeah? And therefore, in your culture, you might observe that more and more the non-plasmid carrying bacteria overgrow the plasmid expression ones. As, of course, having the plasmid producing the protein requires energy because you have to produce more than the other cells. So therefore, cells without plasmids usually are better and can grow faster. If, of course, we have to take into account you are under selection pressure. But if you neglect the selection pressure, without a selection pressure, a plasmid less variant will grow faster than a variant with plasmid. And now you can pack that in some simple examples where you have the growth rate in the presence and absence of the plasmid, and you have here the rate is of course the specific growth rate, present absence of plasmid, and the biomass concentration in present and absence of plasmid. And then you can simply integrate this equation. Rx is equal to dx dt. So that's what our basic equation was already for our Monod-based description of the exponential growth phase. And we get this equation. So of course the expressions get a bit larger because you have always this with and without and so on, but we don't care too much. It's a straightforward approach. Principal parameters are the specific growth rates in the absence and the presence and absence of the plasmid, and the likelihood P that you lose the plasmid. Now if you relative growth rates, you see that if you look in different organisms, you see that depending on the plasmid, you can have quite substantial differences in the specific growth rate. So you see for a certain plasmid variant in E. coli, the specific growth rate can double if the plasmid is lost, which is of course an enormous difference. Yeah, usually it's more subtle, but this can happen. Okay, now if you look at an example that we have an E. coli strain to produce a recombinant protein in a 250 liters fermenter, probability of plasmid loss per generation is 0.5%. which is sounds not too high. Specific growth rates for plasmid-free cells is 1.4 per hour, for plasmid-bearing cells 1.2 per hour. This is well in the range of these values here. Estimate the fraction of plasmid-bearing cells after 18 hours if the inoculum contains only cells with plasmid. So of course what you do is you simply use these values. Now we have everything here. We simply put that in this equation and we calculate. And that's what at the end what we do. And then you put this in your pocket calculator, and at the end we have that 45% of the cells contains the plasmid. So after 18 hours, less than half of the cells have your plasmid, and of course less than half of the cells will produce your protein. So plasmid stability is an issue, and this is marked with a little man because you don't need to know the calculation path here. It's simply using this bulky formula and putting the values in. However, this needs to be crystal clear to you that the probability of plasmid loss is an issue. And now I have a question to you is it more problematic if I use a plasmid with kanamycin selection cassette or with ampicillin selection cassette? Okay. Now let's see whether we have some more responses, and then we start to discuss. So we have now 11 responses. The majority says the best option is ampicillin. Why? Of course, because you usually use it and you have heard it. The minority says kanamycin, and 1/3 roundabout say it doesn't matter. So what is the correct response? Believe it or not, I asked this question already a couple of times in bachelor colloquia, and I expected the students to know it, because if these were students who didn't work in plant physiology or so, they worked in production and they produced something in production fermenters during their bachelor thesis. And in this case, of course, you have to know what is going on there. And yeah, it's not much happening anymore. So how can you decide it? So of course, I would like to ask you if you have the feeling, well, it's ampicillin or so, you need to tell me why. Now, what is correct? Correct is B. And this is the bad news, is only 17% said B. This is only just one or two students saying B instead of A is not correct. Why? Why does it make a difference using ampicillin or kanamycin? Well, this depends on the mode of action. This would also be a question which I would have asked in these colloquia. It depends on the mode of action. And of course you remember what the mode of action of ampicillin is. Ampicillin blocks the biosynthesis of the cell wall of the bacteria. In other words, it blocks the transpeptidase. You know, it has this beta-lactam ring, blocks the transpeptidase, and that's it. Kanamycin is an antibiotic which influences translation because it blocks ribosomal subunit. So based on the mode of action, you would also say, why should this one be better and the other one than the other one? This is not really clear. Then you need to know what is the resistance mechanism. And for kanamycin, the resistance mechanism is simply if you mutate your ribosomal subunit, then this renders you resistant. Now for ampicillin, the resistance mechanism is a beta-lactamase. So in this case, you secrete an enzyme which degrades the ampicillin in the culture. And this means that if you have an ampicillin selection and you grow your cells, that within 1 or 2 hours, depending on the cell densities, your complete ampicillin is gone. So the majority of time, although you have added 100 micrograms per ml ampicillin at the beginning, at the end of your culture, no ampicillin is there. And it's not just even at the end, this is even after a couple of hours, no ampicillin is there. So the major part of your culture time, you work without selective pressure. And that's the reason why ampicillin is not the best choice for stabilizing plasmids in a production system. And this is something you have to know if you work with production, if you want to express proteins and so on. We tested that ourselves. This is, by the way, often that people have no idea of that and publish papers with ampicillin cassettes. We worked with DNA delivery, so we had live salmonella strains again, where we put in a plasmid, and we wanted to see how stable the plasmid is. And we, without selection in our kanamycin selected system, where we used a PBr322 plasmid, which has a better stabilization, which has a lower copy number, but a better stabilization than the Puck runaway plasmids. It depends also on the origin, on the type of origin. Then we had 80 to 90% of our bacteria still had the plasmid after culture. And this is, of course, also a release assay we did do. Now, other groups use ampicillin plasmids, which is complete bullshit, because if you test your culture in salmonella, you test Puck-based plasmids after overnight culture, in most cases, you might have 10% of the bacteria who still have the plasmid. So plasmid stability is a real issue. And I really want you to take that serious, because this can be a reason why your productivity is so low. You have a clone which is very highly producing, but then you go to your culture large scale and your productivity drops down. Change to another plasmid with a better stabilization, and change to a better antibiotics selection if you don't integrate it. So that's a very important point here. Now we go to production kinetics. Now we talked about growth, but of course, depending on our system, our idea could also be to produce a fermentation product like ethanol, as an example. And then we're interested in how the production kinetics looks like. If we look at the production kinetics, we first have to look at how is this product formation related to energy generation in the cell. We talk about coupling to the energy metabolism. Now we can have 3 types. We have, of course, I could have asked you what metabolite is directly correlated with growth. Of course, a fermentation product is directly coupled to growth and energy production. A fermentation product, as you remember from applied microbiology, from metabolism, You remember it, I'm sure. So you remember that, of course, ATP production is directly coupled to ethanol production, for example. You can say that if you go through this fermentation path, you start with glycolysis, then you remember you have the pyruvate decarboxylase, and then you have the reduction to ethanol. You produce your internal electron acceptor, and you could say per molecule ethanol produced, you have 2 ATPs, per molecule glucose consumed, you have 2 ATPs produced. So it's directly linked to the energy metabolism, and this is true for any metabolites which are fermentation products. And you see here it's the list: acetic acid, gluconic acid, and so on. Now, if you have a product which is indirectly associated with energy generation, these are products in these classes. You have all products which are there in the in energy circles, like citric acid, for example. However, the amount of citric acid formed, as it's a cycle, is not directly related to energy metabolism. So a fermentation end product is directly proportional, more or less, to the energy being produced. Other metabolites which are involved in energy formation but are not directly related are in this class. And of course, finally, there is a class where there is neither direct nor indirect coupling to energy generation, and of course all secondary metabolites fall into this class. Why is this relevant if we do that? Well, we can of course look at the production kinetics and the rate of product formation. And you remember, this is again back to the basic reaction theory. And what we said is also there, it is class 1 kinetics. So the rate of product formation, it's the same as the specific growth rate, is of course proportional to the biomass concentration for the specific rate of product formation. So this equation looks very much the same that the rate of biomass formation. So Rp is Qpx. And of course, this equation is true always, because this is just a definition of the rate of product formation, and therefore it doesn't matter whether Qp is constant or not. We don't solve here differential equation at that point, but of course Rp is the same as the delta P delta. This is the rates we remember in basic reaction theory. It's Rp is equal to dP, the MP divided by dt. That's clear. So and of course Qp can vary during fermentation, and if it's varying, we cannot directly solve this differential equation. That's clear. Now, what is the value of my Qp? Well, Qp can be related to growth parameters like the specific growth rate. That's clear. If there is a direct association with the energy metabolism, because then the more growth I have, the more product I form, and therefore there must be a relation between the specific growth rate and the specific product formation rate, Qp. Now, if there is an indirect association, for example, citric acid and so on, it could be that there is a relation between Qp and μ. However, this will not be a direct correlation. So there it might be possible, but it will be certainly more complex to get a mathematical relation. If you have a secondary metabolite which is not associated to growth at all, you cannot mathematically connect Qp and μ, because this is completely disconnected in this case. Yeah. So that's about that. Now, if we look at a product which is coupled to ATP generating pathways, the rate of the product formation is related to cellular energy demands. So now this means I produce energy, I produce the product. Now I have to think of, for what do you produce the energy? You produce energy for two things. You produce energy for growth itself. So you will form your product when there is growth. However, of course, energy is not just growth. So you have also the case if the cell just sits around, it also needs energy. Otherwise, it's dead. Yeah? And we can set up the following equation. If we look at this, we can say that our rate of product formation, Rp, is equal to Rx is our rate of biomass formation fold the yield coefficient. So the yield of the product formation per biomass formation. This is not necessarily constant, the yield coefficients, but of course this must be the case because we have this coefficient. And then we have also a term plus the maintenance coefficient, and the maintenance coefficient here is the specific rate of product formation due to maintenance, fold the biomass concentration. Of course, the more biomass, the more of this maintenance. Also, this can be variable. Now, of course, I can say Rx is equal to mu fold x. This is always true again. This is, I have no assumption here. I just have then, I'm at the constant volume, I'm at batch, and now I say Rx, and I put that in this equation 1. So this is 1, 2, 2 in 1. And then I have simply Rp is equal to ypx fold mu fold x plus mpx. And of course, this is the same as ypx fold mu plus mp fold x. And if you compare the basic equation, we had Rp is qp fold x. This was our starting point. Then we can say if we compare that, this term, of course, then is qp. So qp is equal to ypx for the specific growth rate plus the specific rate of product formation due to maintenance. So in other words, the qp is separated in a growth associated term and in a maintenance associated term. So this we can do if the product formation is coupled to energy formation. Of course, you have these formulas in your formulary. So a warm recommendation is always be aware what you have in your formulary. Of course, this should now also appear, and this is the case. So that's the point here. And of course, you have this equation also in your formulary. So this is production kinetics. And now we come to the kinetics of substrate uptake. Again, for the production kinetics, the important thing to think of is always, is it associated with energy formation, yes or no? In other words, is it a fermentation product, yes or no? As soon as it's a fermentation product, you know I can couple the specific growth rate, and I can couple the specific growth rate with the specific product formation rate. And this is very important. Keep that in mind. Yeah. We come to the kinetics of substrate uptake. You will believe it. The equation, the general equation of the substrate uptake will look very much the same as the others. And we have Rs is equal to the specific rate of substrate uptake fold the biomass concentration. And of course, this is always true. And of course, this is analogous to the volumetric rate of product formation and the volumetric rate of biomass formation. So this is the same. Now with the substrate, we have to think of where does the substrate go to. So, and this is also always true. The substrate can go to growth. You remember we have in our balancing, we have already done that. We have calculated the maximum theoretical biomass yield and so on. There with our electron balances, we have exactly done that. We have looked where the electrons go to, and this is at the end where the substrates go to. And of course, the substrate can go to the growth, biomass formation. It can go to the product formation, and it can go to maintenance. And so therefore, we need to look at these three paths of the substrate, and this needs to be reflected in our equations. Now, what about maintenance? How much substrate do you need for maintenance? And you see here we have just plotted the specific rate of substrate consumption due to maintenance in different organisms and different conditions. So you see that in the case of Saccharomyces cerevisiae, we have maintenance coefficients, which is as 0.03, quite low in anaerobic conditions. And if we're at 1 molar NaCl, we are higher. Here we have Azotobacter vinelandii. Azotobacter is, of course, as you know, it's not Acetobacter, it's Azotobacter, and Azotobacter can fix nitrogen. And if we have this organism growing and it fixes nitrogen under conditions where it can fix nitrogen, and we vary the oxygen tension, you see we have a maintenance coefficient of 1.5 or at 0.15. This is a tenfold difference in maintenance coefficient. So under these conditions where I have a bit more oxygen, so this is 0.2 atmospheres, means that I have a normal 1 atmosphere air pressure there, because it's the partial pressure of oxygen is 0.2 atmosphere. It's 21%. This here is only a 10% air pressure, so I have a reduced air. So in normal surroundings, I am here, and here I have a 10-fold higher maintenance coefficient. What is the reason for that? Can you explain that to me? Please put the response in the chat. What is the reason that my maintenance coefficient is substantially higher for Azotobacter vinelandii if it fixes nitrogen and you have a normal oxygen saturation, and it's way lower if the oxygen saturation goes down? And if I look in the chat, there is less air means less nitrogen for the bacteria to fix. Yeah, you could say that if the oxygen tension goes down, that also the nitrogen tension goes down. However, if your maintenance coefficient goes down, this means it looks like this is better for the cell. The lower the maintenance coefficient, the better for the cell, the easier for the cell. Yeah, there's a correlation with the pressure and maintenance coefficient, but why? Because it's aerobic and consuming more ATP. In aerobic metabolism, you would expect that there is a higher production rate of ATP. It's the other way around. So if you grow aerobically, you remember citric acid cycle. If you have respiration, you generate per ATP, per glucose molecule, around about 38 molecules of ATP aerobically. And in a pure fermentation pathway where you generate, for example, ethanol, you produce 2. So that's it would be better to be aerobic. Yeah. So there is a correlation, obviously, and it's better if you have a lower oxygen tension, because then the maintenance coefficient goes down. Remember, you want to keep that as small as possible, this maintenance coefficient, because you lose your substrate for the cell just to stay alive. This is what you don't want. You want to give the cell as the optimal conditions possible, that you don't have to buy valuable substrates just for the cell not to be stressed. This is what you don't want. You want to go in production. You want to produce biomass, for example. Yeah, this is the point. So during the nitrogen fixation, oxygen is not favorable substance, so it requires more energy to remove the oxygen. Exactly, because the nitrogenase, you remember, can use also oxygen as a substrate. And if it uses oxygen instead of nitrogen, then you have to resynthesize all precursor substances again. So this is kind of, you intoxicate your nitrogenase with the oxygen. And this is, of course, unfavorable, because it takes a lot of energy then to bring it back to the initial status. Of course, nitrogen fixation already takes a lot of energy, or you even increase it if you have a higher oxygen concentration. That's, for example, if you remember, if you look at the rhizobia and so on, that's the reason why rhizobia in plant cells, they are shielded inside of this plant, and the plant more or less creates an environment in these nodules, and the plant creates an environment where these rhizobia are protected from oxygen. So the oxygen tension is very low in order that they can optimally do their job and fix the nitrogen and don't lose energy to resynthesize the precursors for the nitrogen fixation. So that's the reason why this is such a huge variance. So there is always a biology behind. Of course, here you could say a higher concentration of NaCl, which also leads to a tenfold increase. That's stress for the cell, because this osmotic pressure is osmotic stress, and you need to pump out, increase the pumping out of this NaCl and so on. So also that will increase the maintenance. And the same is true if you go up with your ammonium chloride concentrations here and so on. So this is, as soon as you stress your cell through whatever conditions, your energy required for maintenance will go up. Okay, if I look at what is happening to my substrate, I can say if there is no product synthesis, obviously all substrate which goes into the cell will go into growth and maintenance. That's clear. And in this case, I can write the RS is Rx divided by YXS. This also comes from basic reaction theories with my yield coefficients, remember, plus MSX. So remember, with our yields, we could write a yield coefficient which is defined as minus delta G delta K. And in this case, if we have minus delta X divided by delta S for the substrate which goes into our biomass production, we can write that as Rx divided by Rs. So with this yield, in this case of the biomass formation based on the substrate concentration, we can correlate these rates and connect these rates. Yeah, remember, this comes from this also basic reaction theory and yields. So then we can just write it like this, and we can again say that Rx of course is mu x, and then we get this expression and write Rs like this, and we can put in the Monod equation, and we can then have this equation where we can calculate our Rs based on our maximum specific growth rate and based on the yield coefficient of the formation of biomass per substrate concentration. So this is the equation if I have no no product synthesis. Now, if I have product formation, it depends on what the product formation does. So if the product formation is coupled directly to energy metabolism, then my substrate for growth goes to the biomass formation and excreted product, and my substrate for maintenance goes to maintenance. There is no isolated substrate stream just for product formation, as again, it's coupled to energy formation. So I have two product streams and two substrate streams, theoretical substrate streams, which all go into energy metabolism. So in other words, there will be in my term describing the rate of substrate consumption, there will be no term for product formation itself, because this is already, if I have a term for growth and maintenance, product formation is already completely covered. If there is no coupling, things are different. So then I have of course, substrate goes into the growth, substrate goes into maintenance, but there will be an additional stream of substrate going for product formation, which is not connected then to growth and maintenance. So I will have three terms in this case. And if I have a direct coupling to energy metabolism, again, this is what I said, you have no separate term for product formation. This comes from what we have shown before. The equations we have deduced for substrate consumption in the absence of product formations are, of course, also valid in this case. If I have not a direct coupling to energy metabolism, and I remember I can always use the yield terms, and these are related to the rate terms, I can write it like this. I have Rs is equal to my rate of biomass formation divided by the yield coefficient of the biomass formation per substrate consumption. The same for my product and a maintenance term. If I have a direct coupling, this term goes away. And this is very important, because if you calculate the rate of substrate consumption, you have given YXS, you have given the maintenance coefficient, you don't have YPS and your product is associated with energy production, you don't need YPS because this term gets out. And if you don't remember that, you will get stuck because you start with this equation and forget that there is this link with respect to energy production. Okay, yeah, this is just a legend. And now we come to the final term, determining parameters from experimental data. We have already talked a couple of times about that, so we can go through that quite briefly. However, it's of course of importance here. First of all, we have a look at an example. This is what you do during the lab course and so on, so you're already experts here. The example is a mouse hybridoma cell line is used to produce monoclonal antibodies. The growth in batch culture is monitored with the following result. So this is what we have measured. We have the time and we have the cell concentration. Here we have cells per ml, which is not biomass, but this doesn't really matter. The question is there a lag phase? Is it exponential growth? And we should determine the specific growth rate during the exponential growth phase. And what is the culture doubling time? Well, this is straightforward. And of course, what we do to solve that is also very straightforward. So we copy this data into an Excel sheet. We first look at our concentrations here, and then we do an ln transformation, and I just put it here. So it's equal to ln. Here we go. And then we simply plot it, and we take this chart, and of course now we can put then the legends and so on. We don't care too much at that point, but you see obviously we have an exponential growth from 0 to 3 hours, then the exponential growth is over, and you also see there is no lag phase, so this starts right away. So it's not hours, it's days, sorry. So this algae grows slower, so there is no lag phase here. Yeah, this is response 1. And now, of course, we want to know the slope here. So what we can do is, so we can use this one, and you can, of course, calculate the slope directly. So I can do a calculation like this. In the German version it's Steigung, in the English version it's of course slope, and then I can use these values and these values, and of course I should have the same value here. So I have 0.475, which is the same value as here. If I just do this calculation and I don't plot it, I have no idea whether this makes sense. And obviously it makes no sense, because here we include values which are no more in the exponential phase. We should of course only use values from 0 to 3 hours. So if we do just values from 0 to 3 hours, now things look better. And of course now my term is different. It's 0.6651 instead of 0.475. This is a difference per day. So also in this case we need to restrict it to here. And now our specific growth rate also here is the same value, as you see. And but it is important, please always, if you use regression, always plot the regression line to be sure that you are in the correct area. Otherwise, you have a problem there. So that's our specific growth rate. It's per day, as we have our time is per day. And what was the question again? What is the culture doubling time? Well, the culture doubling time is then just ln2 divided by the specific growth rate. So you see, if you do that in Excel, things are getting quick. So it's around about 1 day, the doubling time. And this is also, you should see that a bit more than 1 day. And of course, you see that if you look at the data. So at 0 hours, you are at 4.5 times 10 to the 5. At 1 day, you're at 8.1 times 10 to the 5. 2 days, 1.7. So it's almost exactly 1 day, and this is reflected here. So you should check it whether this value makes sense. It's more difficult to check specific growth rates, 0.67 per day. Checking that is more difficult, but the doubling time helps you to recheck whether your calculations are correct. So that's about the simple exercise in kinetics. You have done that in the lab course, and of course you know how to calculate the kinetics. Here we used Ln transform data just to calculate the growth rate in the exponential phase. And you remember, the advantage is if we use this Ln transform data, we can use also values which are just correlated to biomass, which are proportional to biomass, as for example the OD. So we can directly, using, if we have measured the OD 600, you can directly put the Ln transformed OD values here and to calculate our specific growth rate. We don't need to calibrate the OD values with respect to the biomass. And that's of course making life easier if we are not interested in the absolute biomasses there. If we just want to compare specific growth rates between different conditions, it's fine just to measure the ODs, which is of course faster. So this is how you can do it. And this is, by the way, in reality, as you always do it, you use, of course, your spreadsheet software or your MATLAB or whatsoever to do the calculation. You don't do that with your pocket calculator, and you don't have this rounding errors in between. That is very important. If you do a calculation, you shouldn't round too much in between. You round then at the end result, because these rounding errors add up at the end, and this is not what you want to. If you log transform this function, you can write it as ln x is equal to mu t plus ln x0. And that's the reason why if you plot t versus ln x, that it's a linear function, and mu then is the slope. So that's clear. And now we come to the homework. So the homework this time is the following problem. We have this exercise in the algae batch growth kinetics. So Chlorella algae are used to produce lipids, and we have different kinetics, and these are the values. So obviously in this case the homework, what you do is you use a spreadsheet software, transfer these values, do the calculations, some calculations in between, or let's say what is rational to go to the next step, you do by hand. And these are the result. And the question is, do the cultures exhibit exponential growth rate? That's easy to respond. Maximum specific growth rate in doubling times for these algae cultures, also easy to respond. Do that in a spreadsheet software. The regression lines, please plot them and include these plots in your final version. And now determine an expression for mu max as a function of temperature during thermal activation of growth. Now, this is certainly the most tricky part. So what you do is you use this Arrhenius equation we have already talked about. So at the end, it's a temperature, the Arrhenius equation gives you a temperature dependency of your rate coefficient or rate constant, and of course your specific growth rate is a rate, so you can use this term and say mu is equal to a constant fold e exponent 2 whatsoever. And at the end, what is important, if you plot 1 divided by t versus ln k, which is in this case your specific growth rate, your slope is minus E divided by R. So this expression here. You don't even need to know exactly what was means, but this means that you get a mathematical correlation of your temperature with your rate constant, in our case specific growth rate, and then you can simply then put in a t-value. If you have this equation, if you vary the t-value, which is of course the absolute temperature in Kelvin, if you vary then your temperature, you can calculate for an unknown temperature where you didn't do the measurements, you can calculate then the specific growth rate. That as an hint for a solution. Yeah, and then you use a different temperature, and then of course finally you calculate what can you produce at that temperature in a 1.6 meter cube bioreactor. One point, this is a bit more calculation, but it's very, very useful, because then you don't just learn how to calculate the specific growth rate, which is quite easy, but you also learn how to use these specific growth rates. So we have talked about this Monod equation, which is in the background, where in this Monod equation, of course, you could calculate a specific growth rate based on the substrate concentration. So what you do in kinetics, in enzyme kinetics, is you start with different substrate concentrations and then measure right away the reaction speed. Yeah, and the problem is this does not work with cell growth. So if you have these concentrations which are close to Ks, are very low. So if I put in my biomass at some relevant concentration, in order that I don't have a too high measurement error, and then I put in 0.5 or 5 milligrams per liter of my sugar, this is consumed within seconds. So before I can measure any change of the cell growth and so on, everything is consumed. It makes no sense. So I cannot assess specific growth rates as a function of the substrate concentration in reality in these settings. This only works if the substrate concentrations are and the Ks values are way higher than for E. coli and for yeast. And this is what you will see here, because the correlation is better. But this doesn't work in the case of E. coli with glucose, for example. What you can do is, what we see in the next week, in the next section, is you can use, for example, systems like fed batch cultures or chemostats. Okay, so this is the homework. So going back to the next chapter. So we are here, we are at the reactor engineering. So this is my favorite chapter, because what we did before is we calculate kinetics and mass transfer and so on, but at the end you work with real bioreactors. And now in this chapter we look at bioreactors, we look at how do they look like, we look at different operation modes in a stirred tank reactors, we look what is the productivity and so on in the real reactor, and we look at other reactor designs. So this is now real bioprocess engineering, and you see that then we still have a chapter on reactor sterilization operation, and we have a chapter on process control and instrumentation and sustainable bioprocessing, and you already have the feeling that we might have the chance to have a look in reactor sterilization operation. We might, with the emphasis on we might have, but we certainly have no chance to look on process control and instrumentation. But nevertheless, let's start with reactor engineering. So this is what you should know in this chapter. And now let's start with basic considerations with respect to reactor engineering. Now, if I have bioreactors, how they actually perform, we have several aspects which go in there. So first of all, it's the reactor configuration. So this means, what type of reactor do I have? Do I have a stirred tank reactor, or do I have, for example, an airlift reactor, bubble column reactor, and so on? So this is one aspect. The second aspect, of course, is how large is my reactor? Is it 300 liters or 200 meters cube? How is my operation mode? Do I operate a stirred tank reactor in batch mode, fed batch mode, or chemostat mode? And how are the conditions inside of my reactor? So this all together at the end goes into my performance. What does performance actually mean? At the end, I want to produce biomass X per day. Yeah, I want to produce 5 tons biomass per year because this is what my production task is. I want to produce 20 kilograms of my monoclonal antibody per year because I want to supply this as an API, as this is my active pharmaceutical ingredient, and this is my need, which I have calculated. And at the end, I need to set up then a system which can do that, of course, in the most economic way. And now, if I look at these parameters, what reactor type to use and so on. So first of all, I would need to look at the value. So if I start with proteins from a mammalian cell culture, the price per ton of that is in the range of $100 million. It's very valuable. If I come with more complex metabolites, then you see then I'm in a range of still $1 million per ton. If you go down to bakeries and single cell protein, you're way lower, and the lowest at the other end is certainly wastewater, treated wastewater per ton of fermentation broth. You are at $1. It would be hard if your wastewater price would be here. So now it depends on what you do and what reactor design at the end you choose based on your value and your need. So if you want to produce 10 kilograms of monoclonal antibody per GMP per year, that's of course something different than producing 10,000 tons of citric acid per year. And this of course will lead to a different reactor configuration, operation mode, and so on. Now at the end, and this is what we will do next semester in industrial biotechnology, you will set up your own process. You will work with a software called SuperPro Designer, where you will where all the mass balance and so on is inside. But the point is, what is at the end your task in a bioprocess is it's in an industrial setting. So this means you need to earn money with your process. Otherwise, your company will be dead. You need to earn money. And therefore, you need to look at where do these costs come from. And you see that the total production costs come from different factors, and it's not just your bioreactor. So of course, if you are in a company, you will have an R&D department, you will have administration and so on, and fermentation and downstream processing is one part. Of course, it's an important part, but it's one part. Don't forget that your company is more than that. This will be brought into this industrial biotechnology seminar. So you will compile everything, and your knowledge in business administration, bioprocess engineering, downstream processing, and so on will then all together be put in this project. Now, you can look at the factors which actually determine the cost, and you see, of course, what you could do for strategies to optimize that. And you see in R&D, you could, for example, maximize speed of scale up and so on. Raw materials, you want to maximize substrate conversion or product yield. The bioreactor operation, you could start to maximize the volumetric productivity by, for example, maximizing catalyst concentration or the specific productivity and so on. So you can do by strain improvement. This is a kind of a decision tree what to do. And the downstream processing is the product concentration leaving the reactor. It's very good if you know what are the different variables you can use for optimization, and how can you now calculate whether this makes sense or not. Well, you know, if it's a time thing, we talk about net present value, but we can also use a return on investment for that. And the cool thing about the return of investment is you can feed in these aspects here. You can feed that directly in the return on investment. Then you can check whether if you maximize now your catalyzed concentration, whether this makes a huge difference or it's better to maximize product yield, for example. And this is return of investment, but this is even, so this is as said here, but it is even better if you use, of course, a net present value where you go for a timed let's say in investigation here. So you can say my maximizing of my product yield. I can achieve then a 20% better product yield, and it takes me half a year. And then you can calculate, is it worth it to invest in this half a year if you calculate a net present value? And of course, you all know that from business administration. And of course, that goes into bioprocess engineering, but because at the end, you need to earn money and you need to make then these decisions what to do. This is just the material flow in a bioprocess plant. This is also important. In a bioprocess plant, it's not just your bioreactor. You have logistics of delivery, you have a media preparation, you have your fermentation, you have your downstream processing, and of course then you have also an outbound logistics, and all together this determines your material flow. And there could be, the bottleneck could be in the incoming logistics. This is also what you need to consider if your raw material is risky to get, and it's a rare raw material and you have just one company. It could be that this is the bottleneck. So you should think of how to avoid this bottleneck. Again, in this bioprocess, in this industrial biotechnology seminar in the next semester, this will all go together. Okay, but this is just for you to remember, because here we always talk about bioreactors, and the danger is always that then people are absolutely focused on it. Of course, a bioreactor is the essential step in a bioprocess because that's the core unit. However, it's not the only unit, and that's what is important. The homework you will get the next time is a kind of, let's say, homework compiling many aspects, and I consider that as the most central homework you will get. Next time the homework is almost a kind of an exam preparation homework, and you will also have exercises for exam preparation, and the last hour we will no more do a lecture. We will really do calculations, look at the homework, and discuss about your question. So in other words, thank you very much for your attention. Looking forward to seeing you again next week. I would even look more forward. I hope in the winter semester we can also see by eyes the seminar. I don't yet know how we will do that. This is winter semester, but you need that software. But for sure that there will be some presence things, because that makes life easier. Okay, again, thank you very much for your attention. Looking forward to seeing you next week. Enjoy the remaining day. Weather is nice, at least here in Würzburg. Enjoy the weekend, and don't forget to do your homework, and looking forward to seeing you next week. Goodbye.